Right now we're going to go over the fifth problem on Unit 7, Worksheet 1, Radial Net Forces and Circular Motion. In class, this is the one problem that we whiteboarded all three parts. I'm going to go over those problems in case you weren't here or in case you want to go over these answers again. So, for all three parts of problem number 5, we have a roller coaster cart traveling along a track. In part A, the roller coaster is moving along a level track. The question is, should the forces perpendicular to the track be balanced? If the forces are unbalanced, explain why there is a net force and the direction of the net force. Well, we can see that the cart is sitting on the track itself and the track is level. The first force we should draw for a force diagram is going to be the force of gravity, pointed down. Force, gravity, on the cart by the earth. Because it's touching the track, we have another perpendicular force, normal, pointed up. Force normal on the cart by the track. Now, because it is a flat track and we can assume that the cart is moving at a constant speed, there's not going to be any change in movement up or down, so we can say that there is going to be a balanced force. So I'm saying that those two are equivalent to each other. Part B is to draw a force diagram from a side view for the roller coaster traveling over the top of the hill. Now, it's the same question, should the forces perpendicular to the track be balanced or not? Well, the first force we should always draw is going to be our force of gravity. Pointed down, force of gravity on the cart by the earth. And I'm going to say that's equivalent with the previous force of gravity because I'm assuming it's the same cart. But now it's, should the forces be balanced or not? We can see that when it's traveling over the hill, there is a curve. And if we were to just continue this curve all the way around, we could say that this is going to be circular motion. We know that in circular motion, we have our acceleration pointed to the center of our motion. And from Newton's second law of motion, we know that the net force acting on an object is the mass times the acceleration. So if our acceleration points downwards, so too must our net force. So that must mean that the downward force, the force of gravity, is greater than the upward force, force normal, in this case. Which is why we can say our net force or our centripetal force points down. Now, for the last part, part C, we have that same roller coaster cart, but it's now traveling through a valley. Same thing, we're going to start off with a force of gravity pointed down, same size as the previous ones. And because it's at the bottom of this circular motion, we're now going to say that the acceleration vector points up. So our net force should also be pointed up, or the centripetal force acting on the cart overall will be pointed up. That means our upward forces have to be greater than all of the downward forces. So in this case, our normal force is bigger than our force of gravity. And that is really the three force diagrams we will see for problem number 5. When a cart is moving along a level track, the perpendicular forces are going to be balanced. For parts B and C, when we have a cart undergoing circular motion or traveling along that curved path, because the direction is changing, that means that there is going to be some acceleration pointed towards the center of that curve. And because that's where the acceleration is pointing, that's where the net force or the centripetal force is pointing, so our force diagrams represent that.